Good morning, and good afternoon and good evening, wherever you're joining us from. Thank you all for joining us for the CANSSI Ontario Statistics Seminar. It's also known as the CAST Seminar. My name is Elfrida, and I am a second year PhD student in the Department of Statistics and Mathematics at Brock University. I'm also the Brock representative for CANSSI Ontario and a member of the organizing committee of the seminar. So CAST highlights innovative research in statistical science, both theoretical and applied, from Canada and around the world. These seminars give participants the opportunity to engage with leading experts and deepen their understanding of current research in statistics. So today's seminar is a collaboration between the Department of Statistics and Mathematics of Brock University and CANSSI Ontario. That's the Ontario Regional Center of the Canadian Statistical Sciences Institute, sorry. And it's my pleasure to introduce our special guest. That will be our guest speaker in the person of Professor Himchan Jeong. Professor Jeong holds a PhD in mathematics with a concentration in actuarial science from the University of Connecticut. He also holds a degree in statistics, a master's degree in statistics, and degrees in bachelor's degree in business administration and mathematical science from Seoul National University in South Korea. He is also currently an assistant professor at the Simon Fraser University, Canada, and he is a fellow of the Society of Actuaries. He has published more than 30 peer-reviewed articles in leading actuarial science and statistics journals. He also has received funding in NSEC, among other reputable institutions. His current research focuses on predictive modeling for rate making and reserving in property and casualty insurance. Please join me in welcoming Professor Himchan Jeong. Over to you, Professor.
You so much for your kind introduction. Yeah, it's my honor to be a speaker for today's seminar. Thank you so much again. So, this is one of my research work, which was published in IME in 2024. And then I know, in fact, in Canada, many people know actuarial science, but I prepared these slides for a more general public, not only for the actuarial science people, but also like more wider community of statistics. Then, so I tried to approach this talk because mainly I'm working on actuarial science, but how can I introduce my research to a more wide audience? So I tried to think about possible similarity between like biostatistics and actuarial science. For example, they share similarity in content, like so both are interested in life expectancy, for example, and also they can explore healthcare costs simultaneously and compliance. Yeah, in both, compliance is super important, right? Because for any kind of research, biostatistics research in Canada, it shall be governed by the norm of Health Canada, and also for actuary science, for the insurance companies' operations are also governed by OSFI in Canada too, right? And methodology. So both utilize like commonly shared methodology like web analysis, multivariate analysis, and longitudinal data analysis. In fact, we focus on those two, multivariate analysis and longitudinal data analysis for today. So let me introduce the characteristics of insurance claim first. So non-normal means the responses from the insurance claim data set, they don't follow normal distribution. They follow, for example, in terms of frequency, the number of claim, then they could follow any kind of discrete random variable, discrete distribution, like the number of outpatient visits, because the support is 1, 0, 1, 2, 3, 4, etc., right? About the severity or total charge for each visit. So it would be positive and continuous. So there is no way that we assume that such variable would follow normal distribution and compound losses, like annual healthcare expenditure. So if you sum up the individual healthcare expenditure for that year, and virtually if there was no visit for the healthcare, then the lowest cost would be zero, right? Otherwise, it would just accumulate up to a positive value so that it can take value between exactly zero and any positive continuous value, right? And also for insurance claims, we have a few coverages. Like think about the case apply for when you ask for a quote from the insurance company for your auto insurance. They ask a few things, right? Your age, your gender, your region, your car capacity, etc., right? So it's low dimensional coverages, while there are so many policyholders for the company in the portfolio, and they may offer various types of coverage within the same policy, like a medical, dental, drug, for example, for the health insurance. And it is possible that the same policyholder is observed for multiple periods, right? So if you combine all those four, we need a non-normal regression model for multiple responses observed longitudinally. So we deal with the non-normalness by Tweedie family, and we deal with the regression model at GLM type, and we deal with the multivariate responses observed longitudinally via pos possibly correlated random effects. So as a remedy, we propose Tweedie GLMs with multivariate random effects. So these are the indices I's for the policyholder, T's for the time, and J's for the types of coverage. So for ith person at time t, we have multivariate claim. So for the first coverage, second coverage, and then last coverage. And you also have the characteristic like gender, age, etc. for the person at time t. So this is the structure. So the condition expectation of claim for a specific person could be decomposed into two parts, theta and eta. Theta is a random variable, latent variable, so it captures unobserved heterogeneity. So what do I mean by unobserved heterogeneity? So it's like when you drive, so for example, for auto insurance, when you drive, unless there is a specific device, the insurance company, there is no way that they know how you drive exactly, right? So for example, you may tend to drive very aggressively behind the wheel, but they never know, right? So that kind of behavioral things could be captured with this random variable, unobserved heterogeneity, whereas your gender, age, vehicle capacity, so these are all observable, right? So they are captured via a regression model, observed heterogeneity in this fashion. And then for the modeling perspective, remember that I mentioned non-normal responses, so we do need Tweedie distributions. So Tweedie distributions are in fact members of the so-called exponential dispersion family. They have three parameters. So there is they are characterized by three parameters like mu, the expectation, power, and dispersion. So the main characteristics for the Tweedie distributions is their mean is mu, and their variance is mu to the power of p times dispersion. And it includes lots of interesting cases. For example, if p equals 0, then it includes normal dispersion. If p equals 1, it's Poisson, especially when the dispersion is 1. If p equals 2, it's gamma. If p equals 3, it's inverse Gaussian. And if p is in between 1 and 2, it's component Poisson gamma dispersion, like this fashion. So we're going to assume that z given theta follows Tweedie dispersion, like that way. Then again, the conditional expectation is decomposed into two parts, eta and theta. So by using the Tweedie family, we can handle the non-normalness of the response variables. But how about like those two following properties, multiple insurance coverage and repeated observations of the same policy over time? We're going to use then correlated latent factors to handle such properties, multiple and multiple responses observed longitudinally. So here we have latent factors or random factors, but multivariate latent factors. So we have theta 1, theta 2, all the way to theta j for the same person I over time. And so these are like technical assumptions for the multivariate latent factors. Then note that we didn't assume any distribution for the latent factors. We just assume the moment. So first moment, a second moment, and their possible associations. That's all. So in that sense, such model specification is referred to be semi-parametric credibility, which means the claim distribution, sigma theta is specified as a probability distribution, but theta remains to be distribution free. And any questions so far? If you have any question, you can stop me. Yeah. So now it's time to review the usual auto insurance coverage. First time, so I categorize them into liabilities and non-liabilities. Firstly, liabilities, we have two main types. First one is BI, bodily injuries. So what is liability? Auto insurance liability. When you drive and when you hit someone and injures that person, then you are liable for that damage, right? On his or her body. So you have to cover the medical expenses for that injured, the lost wages and legal fees if you cause an accident. And property damage. Note that it doesn't cover your own injuries because it's liability. And property damage. If you hit someone's property, like vehicle, fence, or building, then you afflict damage on that property, right? So you are liable for those damages. And if you have BIN and or PD liability coverage, then your insurance company will reimburse the damage on behalf of you, right? So these are the liability types coverage. And non-liability type coverage. It's comprehensive. So it covers damage to your own car caused by non-collision events like theft, vandalism, natural disasters like hailstorm, animal collision. And collision is like, suppose you had an error during your driving and you made an accident against the wall or fence, then it could cause damage to the wall, the heated object, but also your own car, right? In the case, you might want some kind of coverage that provides you an opportunity to fix your car with some support, right? So those coverages be helpful in those cases. Well, we're in Canada, right? So you guys know this poor animal. This is a moose, right? And somehow after the accident, the moose broke into a car. And then you can see the car is totally broken. And assuming that that moose is at fault. And the problem is the moose doesn't bear a liability, right? So you cannot sue the moose. And I bet the moose is uninsured, right? So there is no way to get reimbursement from the moose or its legal party, right? Or the associated legal party with the moose. So in that case, there is no way the liability coverage works for your car. But if you happen to have like comprehensive coverage, because it covers the damage from the animal collision, then if you're fortunate enough to have the comprehensive coverage, then it would cover your damage and your car could be fixed. Otherwise, well, good for you. You just need another car out of your pocket, right? So that's why we need different types of coverages, including liabilities and non-liabilities. So assuming that we have three types of coverage in your policy, because mostly liabilities are required coverage when you go for an insurance, but the non-liabilities are optional. Suppose for a person in the policy, there are three types of coverage offered. So BI claims, bodily injury, property damage, and comprehensive. So we have three types of coverage. And then over time, the same company observed the same person over time from year one to year T. And then the multivariate hierarchical claim model described the association in the fashion. So BI claims over time are affected by theta 1 simultaneously. And PD property damage claims are affected by theta 2 simultaneously over time. And the comprehensive claims are affected by theta 3 simultaneously over time by theta 3. And possibly theta 1, 2, and 3 are associated. And then by having the association between among those three random effects, you may capture possible association among those claimed. So this is a way to model possible dependence for the multivariate responses observed longitudinally. So in fact, we can apply the same framework not only for the auto insurance but also for biostatistics. So not sure whether I'm not a biostatistics person, and then as I know, based on my shallow knowledge about biostatistics, mostly they are not super interested in the prediction. But suppose they still they can observe, they can do some research about the metabolic syndrome signs like HDL, the cholesterol, right? And also fast glucose and blood pressure. So those are important measures for the metabolic syndrome. So we can observe the same person over time about the HDL, and we can observe the same person, the fast glucose multiple times. And also we can measure blood pressure multiple times for the same person. Then we can assume that because of the specificity of the person, the HDL over time, observed over time, will be affected by theta 1. And for the person, the fast glucose level could be affected by theta 2. And we can also assume that blood pressure for the same person could be affected by theta 3. And we can later assume that those three factors are correlated, the latent factors. But that's how we analyze the HDL, fast glucose, blood pressure simultaneously, even if they are observed over time. Any questions so far? If not, then I'm gonna just proceed. So recall that we have the structure, this kind of technical structure. Expectation of z given theta is decomposed into two parts. Eta times theta. So eta is what? E3 x gamma, and 8 it captures observed heterogeneity via the regression coefficient, and theta captures unobserved heterogeneity. So our main interest is to approximate Bayesian premium, right? So which is also known as the bonus malus factor. So what is bonus malus factor? So before we proceed, let's recall the conditional structure of expectation of z given theta. So it is decomposed as a product of eta times theta. And because eta is not relevant to theta, you can just take eta out of the integral. So eventually, you just need to evaluate this integral expectation of theta with the posterior distribution of theta after you observe the past data. So this is the usual Bayesian setting, right? But in terms of Bayesian setting, the problem is unless you are super lucky, like you have conjugate pair of the distribution for z given theta and theta, there is no way to obtain this posterior density in a closed form, right? So you may consider, okay, it is usually not feasible to obtain a closed form of the posterior density. So should we consider MCMC instead? The problem is the most significant problem with MCMC in this case is scalability. Why? So here I omitted the index, but we track multiple policyholders, right? So we have to estimate like theta ij. In fact, for one person, we have multiple random effects. We have multiple people, which means if you want to ever use the MCMC, then the number of objects to be tracked is super large. So if you increase the number of people, the sample size, then the number of probability increases proportionally. So that expected that the computation time with MCMs would increase proportional to M, and M could be more than million in some cases. So it is not feasible to try to estimate theta via MCMs in this case. So such phenomenon has been a motivation to develop an efficient approximation method for actuarial applications. So, and how can you efficiently approximate this Bayesian premium expectation of theta given the previous history? So for that, firstly, I introduce a statistic. So a statistic which is called Z star. Z star is defined in the fashion. What is sum of Z times eta divided by what is sum of eta, and this eta to the power of 1 minus p divided by phi is the weight. So Z star intuitively means sum of past actual claims divided by sum of past expected claims. So, okay, let's see. So if you have more actual claims than the past, the expected claims, it tells us that a posteriori, you have been proved to be a riskier person, right? On the other hand, if you happen to had less actual claim than expected in the previous years, then it is proven that you are proven to be less risky, right? So this Z star could be a diagnostic. If it is greater than 1 or greater than 100%, then you're a risky person, more risky person. If this Z star is less than 100% or less than 1, then you're a less risky person. Does it make sense? So, and we have some properties because if you look at Z star, then Z star looks like the potential expectation of Z star given theta is theta. So, Z star serves as an observable proxy of theta because expectation of Z star is the same as the marginal expectation of theta, which is 1. So somehow Z star is distributed similar to theta. So on average, the relative level of unobserved heterogeneity would be 1. But depending on your personal history, it could be greater than 1 or less than 1. So it is tempting to use Z star directly as an estimate of Bayesian premium, but it could be too noisy, so you need some modification on Z star to be used, and the following theory justifies that modification. So recall that we tried to find this Bayesian premium, and it would be too much to do this kind of general optimization procedure. So instead of looking for the Bayesian premium from a general class of function, look for the Bayesian premium out of the class of limited functions, limited size of class, which is linear functions. So out of linear functions, we look for the best linear function that approximate the future claim. We're looking for best linear bias estimator. And the argument is simple, right? We just minimize this expected sum of squares. And then this is well-known risk square problem statistics, right? So we also know the solution. As long as we know the correlation structure, it can be solved in this fashion. Like remember in the regression analysis, we know the solution of beta hat is x transpose x inverse times x transpose y, right? Like that fashion. So as long as we know the covariance and variance, we can easily obtain this linear credibility premium formula, multivariate version. And but isn't it done for now? And in fact, such a form can be written in a more succinct way if we further assume the exchangeable correlation. So exchangeable correlation means recall that we had multiple combinations, right? Multiple random x, right? Theta 1, theta 2, theta 3. And then technically speaking, we can have up to 3 correlation coefficients, right? Between 1 and 2, between 2 and 3, and between 3 and 1, right? So technically, you could have 3 correlation parameters, but if we assume that they are It's just the same, or all the correlation structures are determined by one constant. That's mean that's really what I mean by the exchangeability. Then we can reduce or we can simplify this equation 5 in a more succinct way and with some more intuitions. So, okay, this is the main theorem. So if you assume that the correlation structures are determined by one constant, then the credibility premium can be written as a product of two terms, blue part times red part. So red part captures what? The observable heterogeneity. So as long as you have the same X, this red one would be just same. But blue part is totally based on what? Your personal history. So if you had more claims compared to expected in the previous year, then this blue part will be greater than 1. So you're going to get surcharge. If you have less actual claim than expected in the past years, and you're going to get the discount. So the 8, this blue part tells you the discount rate. So this red part is the base premium, and blue part is discount or surcharge rate. So if the surcharge rate is 1.2, then it tells us that, okay, you have to pay 20% more than your base premium. And if the blue part is 0.8, then it tells us that, okay, then you only pay 80% of the base premium, or you get 20% of discount from your base premium. So that's how you determine, the insurance company determines the modified individual premium based on their personal history. So there are some intuitive explanations. So, and you can see that Z star here, Z star J here, Z star J prime here. So the claim experience from like J's line and also outer lines both affect the credibility premium simultaneously, right? And if you do the math, and then if you plug 1 in Z star Z and Z star J 1, so everything is 1, then this whole blue part is 1, which means for a standardized person, if the expected claim, previous claims, and previous claims are actually the same, then this whole blue part would be reduced to 1. So that means, okay, you don't pay more than base premium or you don't pay less than the base premium. You pay exactly the same as a base premium because you made exactly the same amount of claim in the previous years as expected. So that's the interpretation. And we have some parameters to be estimated from the data. For example, VJ. So as an extreme case, if VGs diverge to infinity, what happens? All else being equal, if VGs go to infinity, then this whole part would converge to 1. So in that case, regardless of your previous behavior, if VGs goes to infinity, then this blue part would converge to 1, right? So VGs goes to infinity, that's the case where you ignore the random effects or you ignore the association of your driving history from the previous year to the current year. So if VG goes to infinity, then the past experience becomes not credible, becomes negligible. So, but we don't enforce the value of VG on our own. They are estimated from the data. So that's the value of this theory. So, and then someone may argue, okay, isn't it too restrictive to have this kind of correlation structure? Which means you assume that all the correlation coefficients are just covered by one constant. That's a valid question, in fact. But still, this equation 6 covers many interesting special cases like this. So for example, if we have two random effects, if we have two coverage, then in fact the structure is covered by one correlation coefficients, right? And then naturally the biweighted inequilibrium premium can be explained by the proposed estimates, right? Estimator. Because mostly for the multivariate literature, we often discuss the theory, but lots of applications are end up with just variability case, right? So in the variability case, we naturally have this kind of form. And for univariate case, what is univariate? Univariate means, okay, we assume that theta 1, theta 2, they have no associations. If we break the association, then it is easy, like if we just said all the correlations are 0, then we could easily break the associations, and then it's reduced to the univariate linear credibility premium case. So for this case, for getting the credibility premium, we utilize Z star J. We don't utilize G star J prime. So for the specific coverage, like property damage, you only borrow information from the property damage. For the BI, you only borrow information from the BI claims. And this kind of credibility premium has been explored extensively in the previous literature. And shared linear credibility premium, which means it's like this another extreme case where you assume that random effects are in fact the same, which means theta 1, theta 2, theta 3, they are identical. So in that case, they could be statistically speaking, the row, the regression, the correlation coefficients are just 1 for everything. Then to compute the credibility premium, we just sum up all possible Z star G. So regardless of the type of variance, type of coverage, you just collect all the information from the other coverage with perfect correlation. So we have shared linear credibility premium, univariate linear credibility premium, and bivariate linear credibility premium as special cases of the proposed estimate. So, any questions so far? And we are working on a statistical model, right? And when we are only given data, there's no way to know like what is V, what is eta, all the associated parameters, right? So those parameters should be estimated. So we have two steps. Firstly, we estimate the fixed effects, power, and dispersion parameters. So for estimating the fixed effect, firstly, we ignore the correlation structure so that we just fit simple to GLMs. So it's like treating all the observations are independently. So you ignore the possible correlations from the multiple coverage or possible correlations out of the repeated measurement structure. So it is less efficient, but usually acceptable because we have super large sample size. Call that for insurance application, the sample sizes could be up to million or more than million. And then if you have so many samples, then even the marginal TGLM works pretty well. And once we have the estimated fixed effects, power, and dispersion parameters, then we estimate the covariance matrix for the latent factors. And then recall that we didn't assume any structure, distribution structure for theta. So we're going to use method of moment estimate to estimate the rho and also estimate sigma using the method moment estimator. So here's a simulation study. We assume that we have three types of coverage, and these are observed for 6 years. So first 5 years are used for the train purpose, and the last 6th year are used for the auto-fit validation. And we have some covariates and different coefficients. So with that said, we compare the following method to compute credibility premiums. So note that we use the same way to compute this base premium, eta. So eta is computed in the same way using the 2D GLMs for all methods, but all the difference comes from what? All the difference only come from what? Come from this way of computing the credibility factor. So naive means we assume no correlation at all, zero correlation at all. So everything is just IID, just like 2D GLM. And univariate means, okay, for J coverage, we take care of the previous claim history, but only for date coverage. So implicitly assume that there's no correlation among different types of coverage. And shared is for date coverage, we just gather all the information from the all types of previous claims. So it implicitly assume that rho is 1. The proposal is like, as we have seen, we adjust for the possible correlation using this method. And true is, so what is true? Because we are doing the simulation, in fact, those theta values are available in our computer. Even if they are in practice, we never know what is true, right? So we can compare. So true shall be the best. And then we want to see, then what will be the second best that follows the true method, right? And this is the summary of 100 times of simulation. And then we can see that gamma 0, gamma 1, gamma 2. So they are very close to the true value. So the fixed effect estimations are working very well. And auto-sample validation. So you can see that smaller the better, because RMS and deviance both measures the discrepancy between the true value and estimated value, predicted value. And then you can see the rightmost column, the true with the true method is always the best. However, if you use the proposed method, it's just always the second best. So it tells us that, okay, if the true method is not available, then the proposed method improves all the existing structure. So it tells us that the value of the proposed method. And also I did another study to measure the correlation between true theta and estimated theta. So estimated theta is nothing but this part, the credibility factor, which is on top of this manual premium. So, and then we want to see in general, if the correlations between theta and theta are high, then that's good, right? And in all cases, we have 25,000 observations. So if we happen to have 50 policyholders observed for 500 years, then the univariate method is almost perfect, right? And there's no reason to apply the proposed method. And if we proceed to 500 policyholders with 50 years, then still the univariate is the best, but the proposed is relatively less worse. And lastly, if we have 5,000 observations, but only observe for 5 years, the limited time of observed years, then we do see that the proposed method is better than the others. So when you have lot of policyholders, but limited time exposure, then the proposed method could work very well. And in fact, the first scenario is the most realistic in our life, right? Especially for the older insurance. And then the last one is empirical analysis with the LGPIF data. So we have some categorical variables and continuous variables. And these are the differences between actual data and simulated data. So for simulated data, we assume that all policyholders in the simulated data, they are observed for 5 years, but it's not necessarily true in actual data, right? For example, some people can be observed for 5 years, others could be observed only for 4 years, even only for 1 year, right? That's possible. And for the simulated data, we assume that each policyholder had all coverage in every insurance year. But in the fact, actually, like they shall have the required coverage always, but for the optional coverage, it's not. So for example, with this actual data, I believe this BC, building and contents, are the required coverage. So mostly, almost every policy has the BC coverage. But like IM, CNP, and these are optional coverage. So the proportion with those coverages are quite low compared to the required coverage, right? So we could estimate the fixed effects for different coverages, and also we can estimate the random effects parameters like power, P, rho, and sigma accordingly. And then lastly, because for this data, we have 6 years, but so we use the first 5 years for the training and the last 1 year for the prediction validation, so that we can see that RMSE and deviance, all again, smaller the better. And the proposed method, in most of the cases, the proposed method refines the prediction performance compared to the other existing method, right? So it tells us that, okay, the proposed method is valuable to increase the prediction as well, not only having the good explainable structure, but also have better prediction. So in this article, we consider credibility premium for multiple coverages. So this proposed framework nests many previous results on credibility premium, and it provides an explicit form of multivariate credibility. And the usefulness of the proposed framework in the rate-making practice was assessed by a simulation study and also in back analysis with the LGPIF dataset. And possible extensions. Proposed framework could be applied to any statistical problem where the response variables are non-normal, multivariate, and longitudinal observed. So for initially, I assume that the X is we only have a few coverage. I mean, low dimensional structure to cover it. But if we have high dimensional structure for the cover it, then we can modify the module mean specification so that we using like FFN or tree-based model to train the module means, and with the trained module mean, we impute the one to this dependent structure. And also with the usage of training distributions, we can analyze different types of distribution for the multiple responses. For example, suppose you have a multiple response, but the first one is count, second one is positive and continuous, and third one is non-negative continuous with point mass at 0. So with that kind of combined data, still you can analyze the data using the Tweedie Multivariate Response model. And the last, the future research. So the proposed framework currently assumes that a static latent factor, theta j. So you don't have index t for the latent factor. So it implicitly assumed that, like for Himchan, the driver, the latent factor doesn't change at all from his birth. So it is innate nature of the person. Then it's controversial, right? So when you continue to drive over time, then it's possible that your driving behavior could improve, right? But with this model, it doesn't allow such kind of improvement. And it also implies that like the claim from 20 years ago and the claim from last year would have the same impact on your premium. And it's less realistic, right? So we could incorporate the idea of dynamic credibility model, which means this theta j could evolve over time. Then we need another index, right? Theta tj, and we have to set up like structure that covers that matches the evolution of theta over time. But it requires a lot of extensions and a lot of computational work, so it's an ongoing project. And thank you for your attention.
Thank you so much, Professor Jean. Do we have any questions for Professor? Any questions? No, okay. Thank you so much for your time, for taking out time out of your busy schedules to join us today. And thank you, Professor John, for taking out the time, even though you're not in our time zone currently, you still make sure to commit to the time. Thank you. We really appreciate it. Okay, so Esther, is there any other questions? Any other thing you want us to know? I think that will be all. She's not responding. Thank you so much, Professor. This was very insightful.
Thank you so
But
much. Yeah.
you're welcome.